Hi everyone. In this video, we're just going to do a couple practice problems using the combined gas law. So as we saw earlier in the lectures, if we take the ideal gas law, PV equals nRT, and we solve for the ideal gas constant, divide both sides by NT, we end up with PV over NT is equal to R. And this was true for any gas under any conditions. And so we can state that the initial conditions of a gas, P1, V1, N1, T1, the one standing for the first conditions, is going to be equal to a second set of conditions, P2, V2 over N2, T2. And so this is the combined gas law that we'll be using for the next couple of problems. So this question here states that a gas has a volume of 675 milliliters at 35 Celsius and 646 millimeters of mercury. What is the volume of the gas at negative 95 Celsius and a pressure of 802 millimeters of mercury? N is constant. So let's use our combined gas law. P1, V1, over N1 T1 is equal to P2 V2 over N2 T2. Now, right off the bat, they tell us that N is constant. And so we can eliminate that from our equation immediately. Now, they're asking us what is the volume of the gas under a second set of conditions. They're asking us to solve for V2. And so let's multiply both sides by T2 over P2. And what that's going to do here is it's going to cancel pressure 2 and temperature 2 from this side of the equation, and that's going to give us V2 all by itself. And so V2 is equal to temperature 2 times pressure 1 times volume 1 all over pressure 2 times temperature 1. Now, let's make sure we put everything in the proper place here. Let's write out our variables. Gas has a volume of 675 milliliters. So temperature, volume 1 is equal to 675 milliliters. They tell us temperature 1 is equal to 35 degrees Celsius. We want to make sure that's in Kelvin. So plus 273. It's going to be 308 Kelvin. And pressure 1 is given as 646 millimeters of mercury. And then they tell us that, temperature 2 is negative 95 degrees Celsius. We're going to convert that to Kelvin, plus 273. It'll be 178 Kelvin. And the final pressure was 802 millimeters of mercury. And once again, we are looking for volume 2. So let's go ahead and plug these numbers into our expression here. So we had this. And temperature 2 was 178 Kelvin. Pressure 1 was 646 millimeters of mercury. The initial volume was 675 milliliters. The final pressure was 802 millimeters of mercury. And the initial temperature was 308 Kelvin. And if we're keeping track of units, Kelvin cancels Kelvin, millimeters of mercury cancels millimeters of mercury, and we're left with just milliliters. Now, whenever you're solving these, if you cancel your units and you end up with a unit that doesn't match the variable, you did your algebra wrong. So that's a quick check before you plug it into the calculator. If you end up with like Kelvin, but you're solving for volume, something was wrong and you go back and double check your algebra. So we ended up with milliliters, which is a unit of volume. So we know we did the algebra right. Now let's plug it into our calculator. 178 times 646 times 675 divided by 802 times 308. I get 314 milliliters. And let's double check. Looks like we did it right. Let's do one more practice problem here. Sample of helium gas has a volume of 0.18 liters, pressure of 0.8 atmospheres, and a temperature of 29 Celsius. At what temperature, in Celsius, will the helium have a volume of 90 milliliters and a pressure of 3.2 atmospheres? So let's write down what's given. So they give us initial volume of 0.18 liters. They give us an initial pressure of 0.8 atmospheres. They give us an initial temperature of 29 degrees Celsius. We're going to convert that to Kelvin, so plus 273. And that should be 302 Kelvin. They don't give us new temperature. That's what we're solving for. They give us a final volume of 90 milliliters and a final pressure of 3.2 atmospheres. Now, you should notice here that the units of volume for initial and final volume are not the same. They gave one in liters and they gave the other one in milliliters. So let's convert liters into milliliters real quick. There are 1,000 milliliters for every 1 liter. Liters cancels, and so that will give us 180 milliliters. So it's important to make sure that both volumes are in the same unit, otherwise it won't cancel. So we can use 180 milliliters now, and that should work. So let's use the combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. Now we're trying to solve for T2. So first things first, let's multiply by T2 to both sides. That'll get it out of the denominator. So now we have T2 P1V1 over N1T1 is P2V2 over N2. I'm going to try and isolate T2 here. So I'm going to multiply by the reciprocal of everything else. So N1T1 over P1V1. Do it to both sides. And that will cancel on the left. So we have T2 is equal to P2V2 N1T1 over N2 P1V1. But the moles remain constant, and so we can eliminate moles from the expression. And so that simplifies to P2V2 T1 all over P1 V1. Now let's get a new slide here so we have more space to write. So we had T2 was equal to pressure 2, volume 2, temperature 1 over pressure 1, volume 1. Let's plug in our numbers. Pressure 2 was given as 3.2 atmospheres. Volume 2 was given as 90 milliliters. And the initial temperature was 302 Kelvin. The initial pressure was 0.8 atmospheres. And the initial volume was 180 milliliters. So if we're paying attention to our units, milliliters cancels milliliters, atmospheres cancels atmospheres, and we're left with Kelvin, which is in fact the unit of temperature. So we probably did the algebra right. So if we plug all that into our calculator, 3.2 times 90 times 302 divided by 0.8 times 180, it's 604 Kelvin. Now, they asked for the answer in degrees Celsius. So if we subtract 273, we should get 331 degrees Celsius. Let's see if we did it right. Yep. Okay. So to recap this video, the combined gas law, pressure 1 times volume 1 over N1 times T1 equals P2 V2 over N2 T2. If anything is constant and doesn't change, you can eliminate that variable from both sides. Make sure your units are matching. You have to be in Kelvin. Your volume units have to be the same. Your pressure units have to be the same. Do some algebra to isolate the variable you're solving for. Plug in all your numbers. Make sure your units cancel and get your final answer. Thanks for watching. See you in the next video.